today's chapter, today's discussion, we're going to deal with 4-bar linkages and something called Grashof, right? And this is, we try to make some categories. We're going to see that there's some limitations that exist for 4-bar 4-bar mechanisms. 4-bar mechanisms, you almost think is the very basic mechanism, and that many things can be made out of a 4-bar mechanism. So this comes out of Norton's section 2.07 and 2.13, and we have the analysis of Grashof inversions. And I don't think actually any of this is actually on homework 1, which is kind of disappointing, but it'll show up on homework 2. So here's our nomenclature. We have, let's see, I don't have my tablet here, so I'll just try to write as best I can with this. We have what we consider the crank, right? And the crank is most often is going to be, that's not always true, but let's just for now, we're going to say that this right here, and I'm going to number the ground as number 1. Wow, I've got that weird thing going on here. So the number 2 is going to be the crank right here. So here's the ground, here is the crank, here is the rocker right here, and the rocker is usually number 4, and the coupler is number 3. Okay, so I skipped over the coupler. So there's 3 and there's 4. So this guy is 3. Wow, that's a weird looking thing. And there's 4. Can't tell you why that's doing that. And so that's the typical way that we name these and we number them. As I mentioned in the first class, they show up in a lot of doohickeys and more than you would expect, right? This is like a type of clamp thing right there. And we can extend one of the links, right? Just because this thing is the link, this link could go up to there and then perform some task. And quite often we will actually see like this thing could be like a triangle, and we will take a look. There's something called coupler curves that we will look at very soon, where we focus on a particular point that's attached to the coupler. That's quite often. So right here, this is called a film advanced mechanism, where the coupler has an extension onto it. That's awful right there. That little thing. Okay. The overhead bin. That's a 4-bar mechanism right there. I'll draw that's the ground onto this. Is this PowerPoint available on Blackboard? Well, the notes are available, and they pretty much are the same as the There's a couple additions that I have in the some things in the PowerPoint that aren't in the notes. For the most part, I'm reading off of my notes, which look like this right here, right? So these notes are right here for your typical arrangement, and so in the notes section. But you could see from this, and that's a good segue here, because I can take my the ground right here, and here we could consider this one the crank. When it's this kind of thing, when we're doing it as a repetitive motion type of mechanism, then the thing that we call the crank, it matters, because that's the thing we're cranking on. Quite often, it's the crank is a lot of times is the shortest of the links, but it doesn't have to be. We'll see that here in a second. And like you can see, here's the bass drum mechanism. I showed this conveyor belt thing where we could take a box, and like this is the crank and it's moving, and so this thing is can move between these two spots and dump off this box from one thing to another. Even like a scale built inside a prosthetic knee is actually, it can have a 4-bar, often does have like a 4-bar mechanism that's built in. It's difficult to identify, but that motion, instead of just being a simple hinge, really makes the motion and the possible pain that might be inflicted on the amputee's leg right here. It can reduce that just by changing the subtle motion, because it's really a means of acceleration. as this thing is changing that can have an impact and an effect, right? So here's like a crane type of thing. But so it's just trying to convince you that 4 bars are ubiquitous, which is just a great word. Now, interesting type of thing, just as a mind thought process, that we can transform, like the 4 bar is such an essential thing that we could actually in a way kind of think about a transformation that this crank slider or slider crank is actually a version of a 4 bar just with an infinite effective link right here, right? So you could just imagine, you could see that this between this rocker rocks back and forth between these 2 points, but if it got long enough, that arc would become a straight line right there, right? So it's like an infinite length. I think that's kind of interesting that we have this transformation, or even this like Scotch yoke thing right here. We could see that like we have this sort of arc that's taking place right here, but as that gets straighter and straighter, this turns into, it makes in this, you have like this effective link right here. Now we have this really effective link that's straight. So that's like transforming one thing into another is conceptually. A cam follower can even be thought of as an instantaneous, or at least for a short amount of its rotational life. You can see how from the radius of curvature right here of this follower part right here, combined with the radius of curvature of the cam, and then this follower right here, this, at least for a short amount of the arc of this cam, is an effective link, the coupler link as the thing. Of course, they separate right there. And by the way, when rolling, this is a half joint because it's slipping and it's rolling at the same time. There was also kinematic equivalence, gets brought up in other books. This was just a quick, I just decided to include this. I liked the figure. It kind of showed where this thing was morphing from one thing to another. It was kind of interesting. So here's one of the big topics for today, our good friend Grashof. And we have to make this decision whether a 4 bar mechanism is Grashof. And then once we've decided it's Grashof, we can actually divide it down into subcategories. So this is a good starting place. It also kind of shows us that by categorizing the things, there's certain traits that we can, by the proportions, right? So what we do is we say, we assign each of the links a letter designation, where S is the shortest, L is the longest, P and Q, doesn't matter which one is P and Q, but they're the other 2 links, right? There's 4 links. One's the shortest, one's the longest, and then the other 2 are something else, P and Q. And if it meets this condition, if and when it meets this condition, what it means is that at least one of the links can rotate 360 degrees, right? And so that's desirable in your most basic of 4 bar mechanisms here. We want that to like turn like this right here, right? We want to have this thing. In this case, this is the crank that's moving here. The green is the ground because G, so they both start with a G. The coupler is the yellow, and you can see the rocker is rocking back and forth. But because of the proportions of this is considered a Grashof. So it's good to start to explore this. So the answer to this thing here is that at least one link can rotate 360 degrees. And the Grashof condition answers the question, will any part of the 4 bar rotate 360 degrees? So that's just one thing here. The shortest is often the crank, but it doesn't have to be, because we can do something called inversions. We can invert which one is the ground, right? So that will change some of the behavior of the thing, but if it is Grashof, it is possible that one can rotate 360 degrees. So here are some of the examples. Let's see. What did I do with the printout that I made? Oh, come on. Seriously? Did I not? I printed this thing out. You got to be kidding me. Where did that go? Maybe I printed it out and I forgot to go get it. Well, I reprinted it out, so we will just deal with it. Okay. Deal. All right. So here's an example right here where we have the shortest length here is going to be length of 2. The longest is going to be 10, and then then that's the ground, and then this one, the coupler, is 8, and then this one is 6. And I think that's pretty close to the one that I just showed in the SolidWorks. So if I take the equation S plus L and then P plus Q right here, and I write those down, all right, identified that's 2 and that's 10. And then the other two, it doesn't matter which one is P and which one is Q. We add those two things together, and what we find is we've got 12 and this is 14. And because that is less than that, it's Grashof. Right? And we're about to classify this, by the way. After we get done deciding it's Grashof, we're going to look at the inversions and make some kind of classification for it. So just to see where we're going, we're going to go to this table right here and make some determination about what kind of behavior this 4-bar is going to do. Right? So first off, we decide whether the thing is Grashof. You can see the first 4 are Grashof, and then there's some other things right here, and then we can decide what kind of behavior the 4-bar is going to make. But we've already established this is Grashof. In the second example here, we take this got a little bit longer right here, and everybody else is the same, right? So this was 2 before, now it's 5. I've extended this, and so just going by this equation right here, or the S plus L, we go the S plus L is going to be 5 plus 10, so we're going to get 15, and let me get rid of that. I don't know why that was, okay, because I was hovering over it. And the P plus Q, well, that's going to be 8 plus 6, so it's 14, right? So since 15 is more than 14, this one is more than that. So you go S plus L is greater than P plus Q, therefore non-Grashof. Sad face. Does that make sense? And did we lose a lot of people? I still only see 9 people out of here. So I see Phil here. Phil made it. So yeah, hello. Okay. Okay. Just double checking in there. I wanted to keep track of what you guys are. So other configurations. Whoops. Yeah, that's why I printed it out for a single side. For example, 3 here. I have to keep my pages. Keep track of my pages right here. Okay, that's page 1. Page 2. Okay. Let's see. We have the S plus L is going to be 4 plus 10, so we get 14. The P plus Q is going to be 8 plus 6, 14. So they're equal to each other, right? But if we go back to our Grashof equation, we could see that yes, it's less than or equal to. So equal does mean that it's going to be Grashof, but what we actually, but it's Grashof, but it's a special case, and we'll see what that means. When this happens right here, we can have some weird inflections that's going to happen when they're equal to each other. And you'll understand this Grashof here in just a second, all right? If you bear with me, I have a demo that will make it 100% clear of why this equation right here that we're looking at, why this equation will just make total sense once you see the examples. This is another one right here where we have 14 and 14, right? And there's two different examples right here. What we call with this one, this is actually a special case that we call a kite. And so you can see that this is the same length as that, and this is the same length as this. So that's where the kite, and now we have over here, and alternatively, this is the same length as this, and this is the same length as this, and so this is a parallelogram, right? And they both have kind of like a little weird behavior to the thing, and it's a lot more interesting when you try it out yourself by making some SolidWorks things, and that makes it's easier to digest. All right, so we're going to come back to these in a second. So when we go to the table here, but I do want to mention this idea of an inversion, right? So we could change which of the links is ground. So like what we've assumed right now is the shortest one is the crank. I said quite often it is, but there's nothing that says that it has to be. So what we could do instead is make the coupler the ground right here, and now this one can rotate all the way, and then this one right here rocks. You can see by the dotted line that this thing has a full 360 rotation, and this one just rocks back and forth. This one, if we make this coupler the ground, this will still go 360, and this will rock back and forth. If now instead we make the shortest one right here the ground, this thing will move can move 360. Not only can this move 360, but this can move 360 as well. That's sort of an interesting. And then lastly, if we make what was over here, what was the rocker, we can make in the original one, we make that ground, this thing will just rock back and forth. Like it does not do the 360. So just because something has the proportions of Grashof doesn't mean that it will go 360. It just means that it has the possibility that something can go 360. And the one that's shown right here, all three can go 360 except for this guy, which just rocks. So here is also some other ones that, okay, so those are the proportions that you saw what we had for a Grashof one. I believe this is a non-Grashof one, and you can see the different inversions that are possible, that these are all double rockers, they call them, because both of the links that are attached to ground rock. And we still have a coupler, and it's doing its own thing. The interesting thing about the coupler is it translates and rotates. Those links rock. Woo! Yay! Woo! So down over here we have these. These are the ones with. This was the parallelogram, if you remember from over here, right? Where that was the parallelogram when. You change. Okay, so its magical thing is that it has two possible configurations that it can flip to. You can just kind of nudge it, and it'll start working in that particular way, and then you nudge it again, and it can work either in this configuration or in the crossed configuration. And here we just brought up the first time this word that we want to watch out for is crossed. And that's going to be sort of an annoying thing that even like we might give someone might give you the proportions of a 4-bar, but there's often potentially two configurations that it could be arranged in, and that's either like in an open configuration or a crossed configuration. So we want to be on the lookout for that as we're going for things. But you could also see that okay, and this is the kite one right here. So this is the kite, and this is the parallelogram right here. Their potential behavior, but a kite one, I believe, if this is the crank, a little flea, what the hell was flying by? So here is the larger. This is called the Barker's complete classification of planar 4-bars. So what you'll see here is this is that equation, S plus L versus P plus Q. And for these first right here, these are less than, right? So these are all the Grashof conditions, all right? And I forgot what these classes stand for here. But now if the link 1, right, so we're numbering these right here, like, you know, as we would be typical. If the shortest one is the ground, right, that means that we have a ground CCC. I'm trying to remember what the CCC was, but it's called a double crank right there. Right, so that what we have that condition, that's this one right here. So it's like crank, crank, crank. Right, so that's why that's ground, crank, crank, crank. That's the double crank, this guy right here. If we have S as the input, the shortest one is the input, that's going to be this one right here, right? That's when, yes. If we have the shortest one is the coupler, I'm going to double check there, right? So here is the shortest one was the ground. Here's the shortest one is the coupler. And so what we're going to get is a double rocker. And if the shortest one is the output, which is this guy right here, right? So we're rocking this back and forth, and that one is supposed to go out. We have a rocker crank, but there's a problem with this one right here. It's easy to get stuck, right? It's better if you have the shortest one be the crank. If instead the input is this guy right here, right? So this is like the crank coming back and forth, like you're pushing it back and forth, and it makes this one rock around. It has the possible to get stuck when this and this get in line with each other. And I will show you that with the finger engine in a second here. Let me go through the rest of these. Looking at the time, 6:37. Yeah, okay. Now we have the case right here. We have another 4 of these where we have S plus L is greater than P plus Q, right? And so now we cycle through what the longest one is ground, the longest one is the input, the longest one is the coupler, or the longest one is the output. I'm looking for you. Place you over there. Right. So here is that possibility here. Let's see if I can move these right on top of there. Okay, yeah, this will work out. So right here, the longest one is the ground. So that is called and all 4 of these are triple rockers, you'll notice right there. But they just decided to go RRR1, RRR2. So there's rocker, 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 rocker. So these all just are all rockers. So that's rocker, rocker 1. If the longest one is the input, right? So I believe they're gonna. I think we're gonna say this one right here. This is the longest one out of these. So if you are like inputting it, that means like that's where the motor is attached, or that's where your hand is pushing the thing back and forth. That's going to be the R2. if the longest one right here is the coupler, that's your rocker 3. And if you have the longest one is the output, so that means that you're like moving this guy back and forth right here. This is going to be the rocker 4. And then as we're going through here, we have this if they're equal to each other, right? So we have, I guess, 6 different configurations right here. So what we could have, if the shortest one is the ground, we have a change point crank, right? And I don't know if I have that written down anywhere. It would be interesting to see examples of that. The idea of the change point is that it could land in either direction, right? It could either it can be in a position, and then it kind of has a choice. So it's really not a good idea to purposely or accidentally make a change point unless there's some specific reason for a specialty kind of thing. So I've seen people make that mistake when they were like building a mechanism because inadvertently, because of some nudge, accidentally goes into a crossed configuration. It won't work the way that you were intending it to. If we have 2 equal pairs right here, that was the parallelogram or deltoid, which was also named, I also called that a kite, right? It was the other name for that. And then if everything is, all of them are equal, you can make a square or a rhombus, I guess, is also possible. So coming back to the ones that we had before right here. This guy, because of the configuration here, let me see if I can move this up a little bit. This guy is definitely a Grashof, but the shortest one is the input right here. So this is technically a GCRR, a crank rocker. Yeah, so I didn't have, okay, so this, and this one is because the longest one is the ground, that makes this one an RRR1 right there, right? Because it's non-Grashof, and the longest one is the ground. This one is equal, right? But it's the special case, and I wrote down what that was, and I believe this is the SCRR, right? So the smallest, that's because the smallest one is the input down here, right? It's they're equal, and the smallest one is the input, so that's an SCRR, a special case crank rocker. I think this is what the SC stands. And then I also write here that this was a, these are both going to be down here with the S2X, the double change point. There's actually one that's a triple change point. That's kind of messed up. So to see these things in action is a lot more meaningful. So I will mess around here with my camera. Here, I'm gonna, I don't know if this is gonna work. I think so. No, it's kind of stupid. I wanted to make like this black background for this, where I come back and it's got lint all over it here. But let me see if this will work right here. I have this mechanism here. Let's see, can this move that far enough back? Right, so I bought this, or I had the UHart buy it for me, specifically for this task, and it came with a coupler that was 85 millimeters long. Right, so if I were to take my handy dandy, boy, this is really well used right here. You could barely read on that. I have another one somewhere around here. Oh, you don't believe me. There you go. I have a fresh one. So in between these two right here, maybe you can read that, is 85 millimeters. And then this is 60 millimeters long. And this is 50. And this one has the input, so it's the crank. And now it came with one that was 85 right here, right? So looking down at this right here, we had 50, 60, and 85. So the one that came with it is, the smallest one is 50, the largest is 85, right? Well, there's two of them there, 85. So the other ones are 60 and 85, right? So there's 135 and 145. So that makes it Grashof, right? And I also printed out an 85 millimeter one. So I'll go put it, the one that I printed out. And I wish we had, I wish there was like a lab as part of this, and we could all do hands-on things. But you deal with the best you can with what you got. All right, so let's see. So you can see that it has this, and it's kind of cool because it has a pretty complex motion, especially if you're thinking of the coupler. The coupler is the most interesting of the in the 4-bar, especially in this configuration for what it does. Let's see, my backdrop didn't work very well, right? I just didn't want the computer monitor behind you, so you could kind of see this a little bit better. And we need to back up a little bit because we're not really quite capturing the whole thing here. So we see that motion. And later on, we will replace that with something that maybe has some kind of point attached to it. Oh, something I should maybe point out here. I could also have attached with those same links, I could have attached it down here. Right, so this is one of the mathematical issues we will see when we go to try to analyze and do a position analysis of a 4-bar. The fact that you could have a totally different configuration, like this is an input. This is like the input angle that we have to the system, and this quite often is considered the output of the thing. But for this, all the same identical parameters, you could have two different results. So mathematically, that's going to cause us like a little bit of a headache, or something we have to be to look out for. Now, I'm going to go back into this other configuration right here, and this is like what's going to come up, I think, in the next class is when we start dealing with coupler curves. If you take a look now, if we put a point onto this, and we could follow, you want to try to follow with your eyes, almost like trace out on the screen what this thing what the point of this thing is doing right there, right? It's going to make like kind of a like not an oval, but kind of an oblong, kind of almost a paisley looking kind of thing, right? And the proportions that you decide on can make a really wide variety of these shapes. Now, if you're going to make a machine that has to do a particularly odd shape, you can look up through a table of these possible configurations, and you can find one that matches the thing that you want to do. And that's a way of designing a 4-bar mechanism, or synthesizing motion, right? That you find a motion that you want to do, and now you can kind of match it up with coupler curves, and then make that point that's on the end of it, make that attached to something that is the task that you want to do. Now, I've also printed out one that was 40 millimeters, right? So if with the standard one that's on here is 50, 60, and 85. So if I put a 40 on there as and between, the shortest one is now 40, the longest one is 85, and then the other two are 50 and 60, right? So the longest one is going to be the ground right here, in between here. But now you can see as we put the 40 on here in between these two, and once again, I could have put this thing on the bottom of it, so there was a different configuration this thing could possibly have had. What you'll see, it can't go beyond this point. Well, it makes sense now. It's because of the length of this thing, right? That this length is too short for this combined with that. And the same thing true when it comes up to there, right? So it can only go between these 2 points. So it's this is a non-Grashof, and because the ground is the longest one, let's see which one does that fall under. When the ground is the longest one, this is an RRR1, a triple rocker, right? If we go back onto our page right here, that is, the ground is the longest one. We see that it's not Grashof, and now we have a triple rocker. And so this is, if you just concentrate on that, it rocks back and forth, it rocks back and forth. Look at this one, it rocks back and forth, rocks back and forth. And even this one, it's rocking kind of back and forth, even though it's rotating and translating at the same time. And then our last configuration here, I have, I printed out one that's, 100 long, right? So now it's going to be the longest one. And so now 50 is the shortest, 100 is the longest, so those together is 150, and the other two are 60 and 85, right? So now, once again, this is 150 and this is 145, but they're really close to each other, and I made that hole too big. So these are almost equal to each other, and I wrote a note to myself, I should have made this 95, because then they would be equal to each other, and that would have been a better thing. But my 3D printer is a sad panda right now. So I would have fixed this, but I am trying to, I'm going to slap it around. But while I'm doing this, I had a question. Did I already show you my videos? Did I already show you that I recorded a bunch of videos? I can't remember because I'm teaching 4 classes this semester. I'm not sure who I told and who I didn't tell. Did I share those with you yet? Anybody want to reply?
This for your dynamic book?
Yeah, for my dynamics book?
I don't think so, but I'll take a look at them.
I think you would have remembered. Oh yeah, the quick return. You know, I think you would say. I'm sorry. I didn't see your chat. I was looking at the population. I wasn't looking at it. I think you could consider it a quick return. I have a quick return. I will show you. I think if you take a look at the thing, it does have a quick return ratio. But this guy right here, you'll see that it actually should get stuck right there. And should get stuck right here, right? So it can almost make a 360, but it gets stuck. But if you push real hard right there, right? So that's because the hole in here is large enough that there's slop right in there. So it's just enough, and it's also kind of skewed out of plane that you can't really quite tell that you can actually have this change point thing there. So like you can see that you go this way, right? This guy can go over the top, but if you go down here, you can see that they both rock together. So that's the idea of the change point right there. That you can't get past the thing. But this is still a non-Grashof. It's just that I've made it like really close to the tolerance right there. But hopefully you can get the idea of I mean, it's a simple thing. It's just that you're adding the two links together, and if one set of them is too long, it can't make its full rotation all the way around. While I'm here, I could also get you the finger engine, which is this thing. And the idea of this is you're supposed to be able to, you know, just rock that back and forth right here. But now this is the shortest one, so it should be the crank, but we're using this as the input right there, right? This rocker. And if you don't, like, if it gets stuck, it can't do it right there, right? When these come in line. It's also be true if you were like pushing this way right here. When this gets in line right there, you get stuck. So my solution was to, there's only one left, is to put nickels on the outside of that. And why do you think that helped? Anybody want to guesstimate why that helped and made it so this thing would, you know, typically, like right now it's not doing it because there's not enough nickels on there. So it's just going back and forth right there because it's getting stuck at its change point and just bumping back and forth. But why do you think that my putting nickels onto there helped?
It provides an external force that is working to move the position away from the position that the machine would get stuck at.
I guess maybe if you were going to if you're going to take an instant in time, maybe that, I think I understand what you're saying, but the simplest explanation is mass moment of inertia and angular momentum, right? When I put the nickels on the outside, it increased the mass moment of inertia, so it had a tendency to be able to get by that sticking point, right? Just like for my little engine that is hiding from me somewhere, and I didn't plan this well on how I was going to show onto this right here, right? But we have our little engine right here, right? And it only has, you know, it in some ways is sort of like a kind of an analogous here, where the crank is often the input. You know, right now the crank is the input, but in reality, the piston is the input, right? That's where the explosion is taking place, and it could get locked down here, right? When the connecting rod, which you can't see because of this web counterweight, when the connecting rod and the crank are in line with each other, it would get stuck right here. But it's got a big flywheel that normally attached right over here, right? I took it off, but it's sitting right over here. And that flywheel, that moment of inertia of this flywheel, which I can't find the get in line with it. Actually, I think I have that backwards. Yeah, I do. That's one of the reasons why I wouldn't assemble. It's got a taper. You're going the wrong way, right? Somewhere in there. Right? Come on. It doesn't matter. Anyway, that flywheel helps to get the thing to turn around and go all the 360 onto the thing. So that's the idea there, where now now I didn't have to time it. Now I have to time it just exactly right, when I'm doing an input onto this, so that I don't accidentally hit it at the wrong spot and cause it to there. So like if I happen to touch it when it's near that change point right there, it'll reverse. See, it's the wrong time. I have other little display thingies right here. I'm not sure what the how this seemed like a good idea when I ordered the thing that I would want it. This is an maybe better to see from here is an offset slider crank right here, right? So most of slider cranks, this right here is in line with the center of the thing. And by the way, the crank it would be considered in this case would be considered the offset between the center of this and that piece right there. You can just barely see it right here. That would be the crank that's as part of this thing. But the offset is that the center about which this thing is spinning, right? It's spinning about this point right there is now not in line with that. And we'll see when we get some various configurations that Norton goes through, that he has. He does quite like he does a lot of the slider cranks, or the crank slider. There's a crank slider because the crank is the input. I keep saying the thing the wrong way. But this is one of the other basic ones, right? We got our 4-bar, we got our slider crank or crank slider, either way you want to see it. And then the other one is a quick return mechanism. And whereas you were saying the other, Sai was asking, is it a quick return? It does have the property of quick return, but this would be not this portion right here, because this is a separate like thing right here. But this crank, right between this crank, this pin, and then this piece right here, this is usually what's considered a slider crank, or excuse me, a quick return. Like, and if I could turn this thing at the constant speed, you would see that it's going to go faster that way and slower that way. Of course, I could just influence it by how fast I'm doing the thing. But if I could make this, if I put a constant speed motor on this, you would see the quick return nature of it. And if you were making like a saw, wouldn't that make sense that you would want like a quick return type of behavior onto it? So there, by the way, this is my Counting Crows backpack. When we bought backstage passes. Shouldn't be able to buy a backstage pass, I think, but that's my opinion. Big Counting Crows fan. So let's see. Okay, so we've talked about that. There's a lot of cool stuff. Here's some of Norton's ancient graphics right in here, but you can see he's got this. This was also this used to come with the book. It might still come with the book. I don't know. But it gave you an idea of the two different or the different configurations right there, right? Depending on, these are the inversions. The dependence on the motion depends on which one of these, definitely Grashof, but which one of these is the ground will change how the thing behaves. The inversions of the non-Grashof right here, I alluded to these, so you could see they're all triple rockers, but they can all do like have kind of weird motion. Like this one looks kind of really crazy. I like this one. Well, check out this one. That's wild. Do it again. I guess this one's pretty wild too. And this is a good thing to think about, these change point. Think about change point as being uncertainty. Like you're not quite sure, because as soon as these come in line with each other, right, it has a decision. Is it going to cross, or is it going to keep going into this right here? So there was our classification. I think I did 4-bar demos. I think I showed, I think it was better. I didn't have these things set up last year, so I think what I've shown was a little bit better with the demos. Right here, I'm going to show some slider inversions right here. So this is a slider crank. Sometimes there's a piston inside a cylinder, but also this little piece can also be on a sliding on a rod. Right here. So here's them showing, and they're kind of confusing with the way that they're overlapping with each other. But you could decide that this is usually where the ground is, right? So this is your typical number one. It's an inversion, but it's like the main guy, right? Whereas this guy right here is if you were to take the shortest one right here. Right, so now you have this slider block has the complex motion. If you take now what you might consider as the coupler instead and make that the ground, you can see that the block, the slider block will rotate, right? And now if you make the block as the ground right here, we keep that stationary. You can now like concentrate on one of them, I guess. Here's the normal one, Here is the one where the that what's normally the crank is now going to be the bearing. So you can see that the slider block has complex motion. So you can see the slider block is translating and rotating at the same time. And I made them in SolidWorks to check them out, right, as well. And this is something we want to be able to use. Let me, when I have this open right now, let me, I think it's this guy's in my way. Where do I go to lift this up? I can't see it now. I clicked, oh, there it is, this thing. There you go, that guy. If normally for your student version, you only have animation and basic motion. It's this motion analysis that we want to use, right? Because it'll be able to do kinematics and kinetics in stuff. So that's why we want to be able to remote log in to the, what are you doing here? Remote log into the lab computers. And unfortunately, the lab computers are pretty slow. So it's going to be a little aggravating. I have to pre-apologize on behalf of the university, or at least for the college, that our computers aren't fast enough. All right, so that was the configuration one. Whoops, no motion study. So you can see now that slider block. Let's see. Will it? It does. You know. Also, we're going to also all have to become much better users of this silly interface thing. I keep forgetting. There's something about creating keys. I think it's this guy right here. You got to disable him and then like disable playback. And I think if you do that and then you recalculate the thing, it'll let you move it anywhere that you want to while it's moving. But otherwise, it's like setting a scene, and it always forces you to go with the same zoom onto the thing. And I always forget to do that. It's a pain. So this is the third one where I'm not sure which one's ground right now. Let's see. Yeah, so this guy, the red one, is ground. And this is really a quick return mechanism, right? So you want to say what's the relationship between a slider crank and a quick return mechanism? This is the quick return mechanism right here. And we will see how to calculate, or AKA synthesize, a quick return mechanism pretty soon.